And I originally planned not to give a talk here because indeed, I gave a colloquium talk about 1 year ago about my scientific work, so there's no reason to repeat it. And I'm also the frequent visitor of KIAS, so I know many people here. But somehow I changed my plan because maybe I need to explain what is role of International Mathematical Union a little bit, because the ICM sold is already 12 years ago, and some younger people may not experience that. And last time, so of course there was Fields Medalists in your heart, but maybe some of you not so familiar with what IMU is doing. So I pick up a particular task of the International Mathematical Union, which is the choice of Fields Medal recipients. And I'm the chair of the Fields Medal Committee, so maybe half of my brain is occupied about this Fields Medal. So that's the reason why I explained. But also, what? This. So this is the first half of my talk, but in the second half, so I switched to my my role as a researcher, and I'd like to explain what happened, what I experienced when I was a young researcher in ICM 1990. So I will record who were the Fields Medalists at that time and what happened after they got the Fields Medal in that field. So that is my plan. Okay, let me go. So first, the question, who is Fields? So he's a mathematician, so who created Fields Medal? That's, I think, most of you knows. But indeed, his main subject was algebraic functions and Riemann-Roch theorems. This is all the subjects, so his accomplishments are no longer recognized, unfortunately. But anyway, so he's a kind of very, very early stage algebraic geometer in the early years. John Charles, JC. But maybe not much of you know that what was the motivation for creating the prize. So in order to understand, of course, he wrote some reports, thoughts about the medal, but somehow it's not so clear what was actually his motivation. So we just imagine what was his motivation by looking at these limited documents. And to understand that, I think it is better to recall the early history of the ICM. So Fields was indeed the chair of the organizing committee of 1924 ICM in Toronto. So this ICM was the first ICM held outside of Europe. So there are several ICM before, but those are all in Europe. And this is the first ICM held outside by Europe. And indeed, the situation was very, very difficult at the time because there was World War I in 1914 to 1918. And after World War ended, there was ICM in 1920 in Strasbourg, in France. But as a result of war, mathematicians from the Central Powers, Germany, Austria-Hungary, Ottoman Empire, Bulgaria, were excluded from the IMU. Maybe I should also explain a little bit of the background knowledge. So IMU has responsibility for scientific part of the ICM now. program, the making choice of the speakers and choice of recipients of various prizes, and local organizing committee does various practical matters. So we have the separation of those roles, but before the war, it was not so clear what was the distinction between IMU and ICM. But anyway, so even it was not clear, but somehow ICM was organized basically organized by IMU. But unfortunately, somehow in between World War I and World War II, that was somehow more complicated situation. So after the World War I, those countries are excluded from the IMU, unfortunately, and they were not invited to ICM 1920, held at Strasbourg. Then somehow there was some tension between those mathematicians in those countries and the countries and mathematicians in different countries, and it was not so easy to hold the ICM. So that was the situation between around the 1920 and 90, yeah, sometimes after. Oops. And because of this tension, 1924, this was the year for the ICM at Toronto, was originally planned to held in US, in New York. But because of this tension, it cannot be held. It ran into difficulties. Then Fields salvaged the situation. So he proposed to invite ICM to Toronto, and everybody accepted that. So it was possible because Fields had many friends in Europe. He was a frequent visitor to Europe, and he was very skillful in scientific politics. So that was the basic reason why he succeeded to invite ICM to Toronto. And this was successful, but it's not really fully successful in a sense because the situation didn't allow him to invite participants from Central Powers. So still they are excluded from IMU, and somehow it was difficult for him to invite because some other people are unhappy if they are invited. So that was a very difficult situation. And this was his compliance with the situation at the time. So he didn't explain the detail of his thought about it, but Senge, I don't know how to pronounce, but he wrote, Senge wrote obituary of John Charles Fields afterwards. And so if you read, so Senge was confident that really Fields wanted to invite all the mathematicians from the world, but the situation didn't allow him to do that. Right? So he had a sympathy with those who are here. So he also understands the problem was basically International Mathematical Union. So they excluded by rule that those countries, mathematicians from those countries. So he had sympathy with those who adhered strongly to the union, and somehow by compromise, as a compromise, somehow he cannot invite people. The situation started to change after the ICM 1924. So at the ICM 1928, next one held at Bologna, so mathematicians, for example, from Germany are invited, and they attended. But that is a very complicated situation. Somehow, so this ICM was not held by IMU. So because IMU is still, yeah, I think IMU at that time are allowed to Germany and other countries to join, but somehow those people still have they hesitate to join. So they are still not in 1928. They are not the member of time. So this is very, very complicated situation. So then, as you know, that eventually IMU disappears before the World War, and ICM, I think, I don't remember the last ICM before the World War II, second, but somehow the international cooperation among mathematicians was not so, how to say, good. So this was a very, very difficult situation. So then Fields began to plan a medal in 1929, so after this Bologna conference, by ICM. And he talked with, as I mentioned, that he has many friends in Europe and other countries, and also US, of course. And he talked with colleagues, also mathematical societies, so German Mathematical Society, so this DMV is German one. And so his idea is somehow, he was accepted by the community. So he, around that time, he wrote he recorded some documents about his opinion on the medal. So it is clearly written, the awards would be open to the whole world. So this whole world means something for him because, as I said, those countries in Central Paris are excluded. So the whole world means actual whole world. And the choice of the recipient must be made by international committee. So this international means actual international for him. And indeed, 1932, the committee was formed, and at that time, Fields died, and but the plan of the medal was the committee of the medal, and also the committee for the medal was formed after his wishes, and the selection of the prize winners was made according to his wishes. So anyway, so if you look at the committee, name of committees, this was international. So Sebeli was the chairs, and Karate from Germany, and Barkov from US, and so on. And also Takagi, he's a Japanese mathematician. He already, he was the member of the first Fields Medal Committee. And this is also from Fields' document. So in making awards for it was in recognition of work already done, but at the same time, it is intended to be an encouragement for further achievement. This is written in one of his documents. And this is the reason why the Fields Medal is awarded to young persons. So we have the age eligibility condition for the Fields Medal. So those. So I will explain what is the exact rule afterwards. So this is under 40 years old, but there's some strict rule what is how you count the age. And also in a document, he also said that this medal should be purely international and impersonal. So it's not quite his idea to name the medal after his name. So, but somehow, I believe that in, so what was it? So in 36, so I don't find the record for the name for the medal in 1932, but in 1936, somehow it is clear this medal is created by his ambition, and there seems to be no other choice to name the medal except calling Fields medal. So anyway, so after that, it is called Fields medal. And as you know, that R. Force and Douglas received medal at ICM 1936 at Oslo. Okay. So now I gradually move to the present situation of the Fields medal. So as I said, Fields said had the opinion that the award should be open to the whole world, and the choice of recipient must be made by international committee. And as I said, at that time, so it's somehow the IMU has had a problem. So here he cannot explicitly say that this international committee must be formed by IMU. But he somehow have a vague idea that this should be formed by some kind of international committee. Now the situation is clear now. So this is the statute of the Fields medal. So the Fields medal committee that decide recipients of Fields medal is chosen by executive committees. This is us. So we already made the committee. So that is happened 3 years ago, yes. So and then the committee was made, and we have lots of discussions. And so anyway, so the committee, chair of the committee is somehow, unless there is some problem, some issue about conflict of interest, it's chaired by the president. So in this case, I am the president, so I am chaired of the committee. And the name of other members remains anonymous. So until the opening ceremony of the ICM, this is secret. And that means that I'm only the person in the committee whose name is public. So any opinions or any nomination is all those correspondence are done through me. So this is my email address, and maybe I ask some of you to nominate the recipients, or sometimes I might ask you the opinions, but this is my role, and I really thank that all the mathematicians who helped me to choose the recipient of the Fields Medalists. Yeah, this is very, very, I mean, I hope that the IMU is, International Mathematical Union is really supported by the mathematical community. So we are not independent from the society, the community, and we are very much supported. And I'm not sure how much it is really recognized, and that was one of the reasons why I really want to see the local people when there's some possibility. So this is very, very important. I think this is important. We are not really upper part of the mathematical community. We really belong to the community, and we are supported by the people. And as I said, so there's age eligibility condition, and this is the original Fields idea that he want to not only recognize the work already done, so at the same time, it should be encouragement for further achievement. So that was original Fields idea. So now this part is basically reproduced in the statutes, and then the condition is somehow made very, very precise. So the Fields medal is awarded to individual mathematician whose 40th birthday must not occur before January 1st of the ICM. So this is very, very complicated, but so basically it should be 40 years. So if somebody's birthday is January 1st, then you must read the rule very, very carefully. Otherwise, basically, it's just before the 40th. And so this rule was set in 1966. People somehow vaguely understand the Fields Medal should be awarded to young people, but there was no written strict rule. So before 1966, it's not so clear what was the consensus. But anyway, so this rule, current rule, can be applied to the past recipients, and all the past recipient satisfies this rule. Okay, this is the promise for the future achievement is one of the difficult tasks for the choice of Fields Medal Committee. Because, I mean, of course, we can understand what is the accomplishment until now, but it is, of course, impossible to predict what will happen in the future, right? So somehow this is responsibility of the Fields Medal Committee to make prediction for the future achievement. So that is, I think, the most difficult task for us. But this is somehow necessary. This is a character of the Fields Medal, so we must really make prediction for the future. So I hope that I will do my best for this choice this time. And but let me go back the history again and return back to 1990. And so there are four Fields medalists: Drinfeld, Jones, Mori, and Witten. So they got the Fields medal, and let us look at what happened after them and after their areas. And I like to check whether this future achievement was achieved or not. I don't want to, so this is somehow it's not my official assessment of this check of achievement. This is really my personal. So because I mean, as I said, I have the responsibility for this coming choice, but because I know that this future achievement is important, so I must somehow, as a personal researcher, I look at this what happened after. And also the ICM 1990 was very special for me because it was held at Kyoto in Japan. And I was a young researcher at that time. And I think that my career was very much influenced after this ICM. So that is also a reason why I check what happened after ICM 1990. So maybe after 30 years from now, somebody look at my choice and maybe have some opinions, and I accept it. But then I hope it will not happen soon. So I hope anybody will not criticize me after my choice will be made. So this is really difficult. Okay, anyway, let me try. Yeah, so as I said, 1990, I pick up a particular year, not a particular field instead. I don't want to focus a particular field. And of course, it is impossible for me to cover all the fields, all development after 1936. And as I said, I was a participant and a career researcher at the time. My career was influenced after that. So this is a photo for the opening, after the opening ceremony. So maybe some of you recognize. So they don't change much. So Vaughan Jones unfortunately died 7 years ago, but other people, yeah, for me, they look almost the same. So as I said, this is not the official view. So this is just based on my personal point of view. And the prize committee was formed by those people. Chair was Dave. So I wrote the nation when at that time. So it was still the Soviet Union. So it's almost, I mean, yeah. Yeah, this part of history I don't recall. And Iwasawa, for Iwasawa, so I'm not sure if Iwasawa is belong to US or Japan. So currently the country for mathematician country is assigned where he or she is working. But for the case of Iwasawa, he retired from US and he was living in Japan. So he was not working at any university. So in that sense, in the current definition of the affiliation, it was not clear whether Iwasawa is belong to US or Japan. So Iwasawa is, of course, Japanese mathematician. But at some point, he moved to US and he worked there. And after retirement, he moved back to US. So anyway, so this is the countries they belong to. So somehow, if you look at maybe a little bit diversity, geographic diversity is not well. So in the current standard, I think IMU discussed a little bit more about the diversity, geographic diversity. So. And there's no female, and somehow the concept of diversity changed since 1990s. That is my interesting observation. Okay, then let me look at individual achievement. So how much time? Okay, the first I start with Shigefumi. Of course, maybe it is not of course. He's a Japanese mathematician. I knew him for many years, and he is a kind of, how to say, the hero in mathematical community of Japan. So there are the three reasons why he received the Fields Medal. So one is proof of Hertz conjecture. I will not explain what is Hertz conjecture, but so roughly it says that round shape is sphere in a very, how to say, easy word. So, but yeah, maybe I don't go into detail. But anyway, so it's somehow, if you hear it as it is, it sounds like a tautology because round shape is sphere. But indeed, this is a very, how to say, indeed it turns out the problem itself sounds a little bit naive. Maybe this is my frank opinion, but the method he used to solve conjecture was very important. And this was the reason why he succeeded to make the so-called, to achieve the so-called minimal model program, which is birational classification of algebraic varieties. So he achieved this in dimension 3. So in dimension 2 or 1, this is very classical subject. So it was already achieved by various people in the first half, at least in the first half of the 20th century. But at that time, nobody believed that such classification is possible in higher dimension. So Mori changed the shape view of in the algebraic geometry completely at that time. And then he also gave a classification of three-dimensional manifold called Fanon manifold, and that was joint work with Mukai. So this Fanon manifold is some kind of special property. So this is first Chang class is positive. And this is a small class of manifold among all manifolds, but still somehow very beautiful classification he gave. So key results, maybe I will not go into detail because, of course, KIAS, there are lots of good algebraic geometers maybe who are much more familiar with those. So anyway, so this key result is a concept which is invented during the proof of Hartson conjecture, and this is turns out to be very powerful and very important. And then, if you look at the achievement afterwards, so you recognize many big advance after 1990. So one famous example is existence of flips. So this is one of the main issue in the minimal model program, and Mori achieved in 3 dimensions, but people did it afterwards. In higher dimension, in arbitrary dimensions. So this is due to Bilka, Cassini, Haikon, and McConnell. So, and Bilka received the Fields Medal with this work and also his later works. So this is very big result, and this influenced in other fields also. And then for Fano varieties, so this is indeed there's some relation between the algebraic geometry and the differential geometry because so you consider some class of Fano varieties called the stable ones. So those stable is a concept in algebraic geometry, but this is equivalent to existence of Kähler-Einstein method, which is a differential geometric concept. And this is the famous Donaldson-Tian-Yau conjecture. And so it was solved by Donaldson and his collaborators and also Tian. So anyway, so this is a big subject which exists in between the differential geometry and algebraic geometry. And this Fano variety, as I said, the classification of Fano was done by Mori and Mukai, and Fano variety turns out to be very important topic, and this is, as I said, this is. And then people start to study the moduli space of Fano varieties, and if you restrict to the stable one, then it forms a nice moduli space, and that is, I think, the big achievement done after the 1990. So, I mean, of course, there are lots of other achievements in algebraic geometry. But I think that somehow the view of, as I emphasize again, that somehow the current view in algebraic geometry for higher dimensions varieties, higher dimension varieties are very somehow follow the lines of original idea created by Mori. So this is, I think this is the, I think this is a fair understanding of current state. Okay, next go to Vaughan Jones. So he's expert in the von Neumann algebras, and so this is most unfamiliar to me among those four Fields medalists. So I cannot say anything about it. But he's also very famous about definition of polynomial for knots and links in 3-dimensional spaces. So this is now called Jones polynomial. So this is very important polynomial, and so I briefly explain how he found this polynomial. But this is knots and links are subject in topology. So many people study, many topologists study. But the Jones polynomial, Jones, as I said, worked on this functional analysis or polynomial algebras, and he is not working on topology at all. So that was very, very, because of that, so the topologists are very much surprised at the time when Jones found this invariant. And this Jones polynomial is very powerful invariant for nodes and links. And after that, this happened almost immediately after Jones, or even before he got the Fields Medal. So because this discovery of Jones polynomial happened in early 80s, and this was led to the Fields Medal in 1990. But in between early 80s and 90s, the people already start to work on the extension or generalization of those polynomials or invariants. And in particular, Witten in 1989 found interpretation of Jones polynomial in using quantum fields. So of course, people, you know that Witten is the theoretical physicist, not a mathematician. So he used quantum field theories is a theory in theoretical physics, which still lack in mathematical foundation, even in the current day. So anyway, Witten found quantum field theoretic interpretation of Jones polynomial, and also simultaneously he succeeded to generalize from R3 to general 3 manifold. And then soon after Witten's work, Reshetsky and Life used quantum groups to make Witten's heuristic argument based on quantum fields to make invariant rigorous. So I will come back to the quantum group when I may explain during Fields' work. So anyway, so this is almost immediately after Jones' work, those developments happened. But still, if you look at the history, still lots of interesting development happened after Jones' polynomial. So one example is Hovanov homology. So this is a refinement of the Jones polynomial. So instead of, Jones polynomial is polynomial. Instead of polynomial, so Hovanov defined invariants valid in graded vector spaces. And if you count the graded dimensions, then it recovers the polynomials. So this polynomial is known to have coefficient in integers. But from the original definition, it's not so clear why this is integer coefficients. But Hovanov homology somehow give a good explanation why they are in integer coefficients. Okay. So next is Edward Witten, as I mentioned already. So he's a theoretical physicist, and he got a prize because of this achievement. So one is supersymmetry and Morse theory. So this is a relatively, so as I mentioned, quantum field theory has no rigorous mathematical justification or foundation. But so this is about the first topic, supersymmetry and Morse theory, is about the quantum mechanics. So that is relatively well understood concept. But still, using supersymmetry, he has a clear understanding of the Morse theory in terms of quantum mechanics. And as I mentioned, he invented the way to understand some topological invariant using quantum field theory. So this is now called topological quantum field theory. And there are, around that time, people understand there are examples of topological quantum field theories. So Donaldson theory was, so Donaldson received the Fields Medal 4 years earlier, so in 1986. And this is, now Witten understand this is an example of topological quantum field theories, and he understands Jones theory as example of topological quantum field. And after that, so this is continue to be a very important topic. So even as I said, the symmetry and Morse theory was originally about the quantum mechanics, which is relatively well understood. But now people apply this way of understanding in the infinite dimensional quantum mechanics, but the target space is infinite dimensional space. So then quantum mechanics change to the quantum field theory. Then it becomes more interesting. And the flare theory is an example of such theory. So this is now understood as application of these first items. So this is, as I said, supersymmetric, supersymmetric quantum mechanics, but the target space is infinite measure. And also, mirror symmetry is very hot topic, and the mirror symmetry is very roughly understood as one example of topological quantum field theory. But it has connection with many areas in mathematics. For example, the mirror symmetry has a big surprising application to enumerative geometry, which was all the subjects in algebraic geometry. But now I think that this becomes very hot topics, and many people working on enumerative geometry. And also, this mirror symmetry connects algebraic geometry and symplectic geometry, which is a field in differential geometry. And this was more, how to say it, deepened by Kontsevich, the so-called homological mirror symmetry. So it predicts some relation between two categories. One category is arising naturally from algebraic geometry, the other naturally arises from symplectic geometry called Fukaya category. And Kontsevich, so I think this Kontsevich received the Fields Medal before this homological mirror symmetry. So this homological mirror symmetry is achievement after, maybe around the same time. But anyway, so this was a very big development. So I think for Witten, there are too many further achievements afterwards, and still the influence of quantum field theory or even string theory to the pure mathematics is still very big, and many more. Even myself, I'm very much, if you remember what I talked last year, then I explained the Lagrange program is influenced by quantum field theory. So this is very quantum field theory, the power of quantum field theory. We still don't fully appreciate. That is my opinion. So anyway, so in the middle, so in 1994, the so-called Seiberg-Witten theory was found, and this is yes, maybe before 94, I must say that this, as I said, so topological quantum field theory is interpretation gives an interpretation of Jones invariant, and also this Leshetsky-Twyf's work. Of course, this Witten's insight was earlier. So in that sense, so this quantum field theory was kind of interpretation of mathematically well-established result. But somehow in 1994, Witten found the so-called Seiberg-Witten theory. This is a revolution in quantum field theory in the context of not relation to mathematical application. And this was, this predicts the equivalence between Donaldson theory and the so-called Seiberg-Witten theory. And the mathematicians somehow switch from Donaldson theory to Seiberg-Witten theory after that, because Seiberg-Witten theory is much more manageable. But anyway, so the connection between Donaldson theory and Seiberg-Witten theory is really application of the power of the quantum field theory. So it's not merely the interpretation, it's much deeper. So I think that this people should appreciate this power of quantum field. And as I said, so now we might have application even for Lagrange program. So I think that this quantum field theories continue to be influential to pure mathematics. That is my personal opinion. Okay, Drinfeld got a Fields Medal by his work on Lagrange program for GL2 and discovery of quantum groups. So quantum groups were motivated by quantum integral systems studied by Fateev and his school. And these quantum groups has application to mathematically justify this Witten's heuristic definition of knot invariance for three-dimensionals that was done by Leszczyński and Trife. And these quantum groups have lots of application to representation theory. So one famous application is Leszczyński and Kashiwara's work on canonical basis or crystal basis. So this is very, very powerful combinatorial tool in representation theory. So many people work in the representation theory working on that. And also there was surprising application of quantum groups to modular representation theory. So this is a very old subject in representation theory. So people studied, so representation of the, for example, a compact Lie group in representation in complex vector spaces were established by Weil and others, and that is the subject in the early 20th century. But the problem is somehow much more difficult if you consider the group and the representation in positive characteristics. So you can change the field from characteristic 0, which is complex numbers, to fields in positive characteristics, and the situation is somehow completely different. And it was a very difficult problem, but in mid-90s, by using so quantum groups lives in between complex numbers and fields in positive characteristics in a sense. So by using the quantum groups as a bridge, so people understand some make a big advance in the understanding of representation in positive characteristics. And of course, I mean, the geometric Lagrange conjugation, this is based on the Drinfeld's proof of this Lagrange program for GL2. So this becomes a very, very important and big subject in representation theory, and many people contribute to development of geometric Lagrange, and several people received the Fields Medal in this direction. Oops. Okay, this is basically my overview of this, what happened. And so there's, I observe I make some observations. So as I already said, that there have been lots of achievements. And also, but I should say that the 3 among 4 are related to somehow physics or quantum field theory. And I emphasize, as I said, emphasize this is somehow quite influential, and still, even now, at the present time, it is still very important. Okay, next Fields Prize will be announced on July 23rd, the first day of the ICM. So please stay tuned, and I will announce the recipients. So thank you very much for attention.